So gas laws, there are quite a few gas laws that you need to know, but you can always put them on a help sheet, and I highly recommend doing that. We're going to start with Boyle's law. So if we hold temperature constant, what we find is that there's a relationship with gas pressure and volume, and what we find that P1 V1 equals P2 V2. So pressure times volume equals pressure times volume. And so one could be initial, two could be final, or it could just be two different pressures and two different volumes. So for this gas law, you can use any pressure or any volume units as long as it's the same on both sides. So the way you can tell that you have this gas law is you're given two pressures and one volume, or two volumes and one pressure. Now a linear graph, you'll notice, is pressure versus 1 over volume, and that's what makes it linear. So here is a practice problem, and what you find with gas laws is they tend to give you lots of extra information. So a balloon contains 30 liters of helium gas at 101.3 kPa. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25 kPa? So what I want you to do is get used to identifying the different variables that you need. So I know liters is a volume, that's V1. kPa is a pressure, that's going to be a second volume, and again kPa is a pressure. By doing this, you'll realize which gas law to choose just by which variables are available. So Boyle's law is P1 V1 equals P2 V2. So we're going to put in all of these variables, and what you'll find is these are all going to be plug and chug, meaning once you know which gas law to choose, we just put in the numbers and solve for the one unknown. So here I found VT to be 121.6 kPa. Okay, so the next law is Charles' law. So this one we're holding pressure constant. What you will find is V1 over T1 equals V2 over T2. Now your volumes could be in any volume unit, but your temperature must be in Kelvin. So to convert to Kelvin, you're going to take degrees C plus 273 or 273.15. For simplicity, you could just stick with the 273. It kind of depends on where you're doing your conversions. So over here on the left, you can see a picture showing Charles' law. And here is a linear graph of volume versus temperature. So we could actually do this in lab and determine this gas law if we had time. So let's try a practice problem. Here a balloon is inflated in a room at 24 degrees C, has a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees C. What is the new volume? So again, I'm going to circle the main things, identify what I have, and I also notice that my temperatures were given to me in Celsius, which means I do have to convert to Kelvin. If you do not complete or convert to Kelvin before you do the gas law itself, you'll actually get the wrong answer. Sometimes I'll just throw it all in one thing here, making sure I include parentheses, just as a reminder to my brain to convert to Kelvin, or sometimes I would just go ahead and convert it there. So this is going to be cross multiplying, solve this one out, and I find that V2 is equal to 4.5 liters. Okay, next law is Gay-Lussac's law. This is actually two different people that came up with this one. Now we're holding volume constant, and we find P1 over T1 equals P2 over T2. Here pressure can be in any units, but just a reminder, temperature does have to be in Kelvin. Here's a little piston picture to show what this law would look like, and notice here it's pressure versus temperature will give you that linear graph. So here's another practice problem. Notice again lots and lots of words. That's typical for gas law problems. So our aerosols cans carry warnings on their labels that say not to incinerate or store in the cans above a certain temperature. The gas in a used aerosol can is at a pressure of 103 kPa. Again, identify these variables at 25 degrees C. The can is thrown into a fire. What will the pressure be when the temperature reaches 928 degrees C? Okay, so P1, T1, P2, T2. And so I would realize to use this gas law because those are the variables that I have. So 103, again, I need to convert to Kelvin. I don't want to forget that. Okay. Now, if your final temperature needs to be converted back to Celsius, you do that at the very end after you have solved out the whole problem. So I found that one to be 415.1 kPa. Okay, next gas law is actually a combination of the three that we've seen. So we had Boyle's law, Charles' law, Gay-Lussac's law, and what you'll find is combined gas law is putting them all together. So here we have P1 times V1 over T1 equals P2 V2 over T2. Okay, so if we held temperature constant, there we go, we got Boyle's law. If I decided to hold, let's say, pressure constant, now we got Charles' law. So you can see how we can figure out the other gas laws knowing the combined gas law. Now at the bottom here, you'll see this comment about temperature must be in Kelvin, which we've talked about, but it also has STP. STP stands for standard temperature and pressure. Okay, so for standard temperature and pressure, it's going to be at 1 atmosphere, which could be equal to other pressure units depending on what you have. So that could be torr or millimeters of mercury or 101.3 kPa and 0 degrees C, which we also know is the same as 273 Kelvin. So sometimes you feel like you're missing information in a gas law problem because they say it's at STP, but the reality is you actually know a pressure and a temperature. So here's a combined gas law problem. The volume of a gas-filled balloon is 30 liters at 313 Kelvin and 153 kPa. What would the volume be at 273 K and 101.3 kPa? What I find with these particular kinds of problems is people are really good at making a math error, especially in the calculator. It's very easy to do. So just be careful inputting things in, double checking those numbers, and making sure you put them in the correct location. So when I solved this one out, I found it to be 39.5 liters. Okay, next gas law is the one that traditionally you'll probably find is the most famous. It's known as Pivnert, or the ideal gas law. Okay, and so this is if you're given one pressure and one volume, one temperature, or moles, this is the gas law we'll choose. What I find that people get confused by is that it has a constant in it, and we're not used to having a constant. So the constant is this letter R. Okay, so that's the gas law constant. And I have this table here to help us know which R to choose. Okay, so I'm going to highlight the ones that we'll probably use the most in this class. Okay. And so those are the ones I would focus on the most. And then if I was to rewrite R, what you'll find is these units here, this column, it just allows for all the units to cancel. Okay, so you're going to choose your R value based off of the pressures given in your problem. Okay, so for example, if I am working in torr, I would choose 62.36. Okay, and if I was to write the units, it would look like liters torrs over mole Kelvin. Okay, so that number, that's 62.36, would go into R, which means my pressure would have to be in torr, my volume would have to be in liters, N is the number of moles, and K is your temperature in Kelvin. Now we could actually solve for units of R to show how this works. Let's say my pressure is in atmospheres, my volume is in liters, moles, R, and temperature in Kelvin. We're going to isolate that R by itself. And that way you can see all these units are just to allow for all these things to cancel out. Okay, and so that's how that 0.08206 R would come to be. So let's try one of these. So this is a little bit more difficult ideal gas law problem. Notice we have one volume, one pressure, one temperature. Whenever you're asked grams or kilograms, you're going to probably have to find moles first. So that's what we're going to do. So we take PV equals nRT. We take our pressure. And I notice that my pressure is in kPAs. My volume is already in liters. It has to be in liters for this particular gas law. We're going to find N. Now R, based off of this unit of kPa, needs to be 8.314, and my temperature is 315. So when I solve for N, you'll find it's actually a pretty large number, which kind of freaks people out, but we started with big numbers. So I found there were 1.3 times 10 to the 6 moles of CH4. And so now we're going to take that 1.3 times 10 to the 6 moles of CH4. We're going to convert that to grams using our molecular weight. Okay. And then we're going to convert from grams to kilograms. And it's still going to be a pretty large number. I want to say it's 2.0 times 10 to the 4th kilograms of CH4. So there are differences between ideal and real gases. Ideal gases would have to conform to kinetic molecular theory assumptions, and real gases differ most from an ideal gas law or ideal gas at low temperatures and high pressures. So I would make sure I'd have that on my help sheet. That's usually kind of a multiple choice style question on an exam. What I want you to think about is at low temperatures, how those gases, those things are going to move a little bit slower, and they're going to get a little closer together. And if they're a little closer together, maybe a little attraction can build. And that's why it doesn't work well, because you want to have those all separated. Okay, next gas law is Dalton's law of partial pressures. So each gas in a mixture exerts a partial pressure. In a mixture of gases, the total pressure is the sum of those partial pressures. So basically, you're just adding those parts to the total. So these are usually kind of fun to do. So air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What is the partial pressure of oxygen at 101.3 kPa of total pressure if the partial pressure of nitrogen, carbon dioxide, and other gases are 79.01 kPa, 0.040 kPa, and 0.94 kPa? So P total equals P of your parts. Okay. So our total pressure was 101.3 kPa. We're asked to find the pressure of oxygen. And I'm just going to throw in the other partial pressures that we know. So if we solve for PO2, we would find that it is 21.31 kPa. Okay, last gas law. Graham's law of diffusion or effusion. So diffusion is a tendency of molecules to move towards areas of lower concentration until the concentration is uniform. Effusion is basically, it's the same idea, but it's escaping through a pinhole. And so what I like to think about is like the perfume or cologne area of a department store. In the center area where that is, it tends to be really strongly, lots of strong smells. But as you get further away, it's a lot less. So that it diffuses throughout the store. Now, gases of a lower molecular weight will diffuse or effuse faster than that of a higher one. So if you think about a sprint between a 500-pound man and a 100-pound man, most likely that 100-pound man would win the race. In the equation here, it's a little bit scarier looking. Don't make this harder than it is. Make B the heavier element and make A your lighter element. It'll make it easier when you try to understand the rates. So let's see what this looks like. Which effuses faster, nitrogen, which is a Hofbrinkel, or helium, and by how much? So we're going to take rate A over rate B equals the molar mass of B over the molar mass of A. So A is helium and B is nitrogen. So nitrogen has a molar mass of 14 times 2 is 28. Divided by the molar mass of helium, which is 4. So we divide those two numbers and take the square root. We find that it is 2.6 times faster. So we find that helium, because that's on top, is 2.6 times faster than nitrogen. Now don't forget, there's lots of good practice here. The gas law is versatile practice. They're all mixed up, so I think that's really useful. I find people need a lot more practice with the ideal gas law. This one is also a little bit of everything. And I suggest checking out CK12 and focus on separate gas laws where you need help. I also have posted some videos that are different than me talking through this to help you as well.